All right, so get ready to dive into some seriously cool cosmic stuff because today we're talking about the universe's very first light.
The cosmic microwave background.
Exactly, the CMB. But, and here's the kicker, we're ditching the Big Bang explanation. We're going beyond the bang, so to speak.
Sounds intriguing.
It is. We're going to be looking at a theory called quantum gravitational redshift.
QGR. A real head scratcher.
It is, but it could hold the keys to some major cosmological puzzles. So for those who might be new to this, what exactly is the CMB? I mean, what are we even talking about when we say cosmic microwave background?
Well, picture this. Billions of years ago, the universe was this incredibly hot, dense soup of particles and energy.
Okay, I'm picturing it kind of.
As the universe cooled, light finally broke free from this primordial soup.
So this is like the very first light that could travel freely through the universe.
Exactly. And that ancient light has been stretched out over billions of years as the universe expanded. And we see it today as this faint glow of microwaves coming from every direction in space. That's the CMB.
Okay, so like a cosmic baby picture?
In a way, yes. A baby picture of the universe just a few 100,000 years after.
Yeah.
Well, whatever it was that came before.
Right, because we're ditching the Big Bang here. And that's where QGR comes in, right? What makes this theory so different?
Well, the traditional view of the Big Bang model sees the CMB as just this fading afterglow of that initial event.
Okay, that makes sense. A burst of light from the Big Bang, and it's been fading ever since.
But QGR, it throws a wrench in that idea.
How so?
It suggests that this cosmic microwave glow, it's not just a leftover from the past. It's being constantly replenished.
Wait, what? Constantly replenished?
Yeah, constantly. QGR proposes that photons, those tiny packets of light, they actually lose a tiny bit of energy as they travel through the universe.
Okay, I think I remember that from physics class. Light and gravity, they interact somehow, right?
Right. So imagine these photons traveling for trillions of years, losing just a tiny bit of energy here and there as they encounter gravity fields from stars and galaxies.
Okay, and what does that have to do with the CMB?
Well, QGR says that this tiny energy loss over these vast cosmic timescales, it could be the source of the CMB we observe. It's not just a fading snapshot. It's like this constant hum of low-energy photons being generated all the time.
Whoa, so it's like a live feed of the universe in a way.
You could say that. And it gets even more interesting when you consider the CMB's most puzzling features.
Like what?
Well, for one, it's incredibly smooth, like surprisingly smooth.
Smooth, what do you mean?
I mean, the temperature of the CMB, it's almost exactly the same in every direction we look. There are these tiny variations, but overall, it's remarkably uniform.
And that's a problem.
Well, it's a puzzle. Because if the universe expanded from a single point, like the Big Bang suggests, you'd expect the CMB to be a lot more, well, messy.
Okay, so the Big Bang has some explaining to do. But how does QGR address this smoothness problem?
That's where things get really interesting. See, in a universe without a Big Bang, without a defined starting point, photons would have had virtually infinite time to interact and spread out their energy.
Infinite time. Okay, now you're just messing with me.
No, I'm serious. Think about it. If the universe has always existed, or at least for an incredibly long time, those photons would have had plenty of opportunities to bounce around, even out their energy, and create this smooth, uniform background we see as the CMB.
So we've got this picture of the early universe, and it's like this perfectly smooth baby picture, almost too perfect, right?
Well, not quite perfect. Remember those tiny variations in the CMB we talked about?
Oh, right. The temperature fluctuations. But those are like, what, really tiny, right?
It's tiny, yes, but incredibly important. They're like little clues hidden within the bigger picture. And QGR actually offers a really interesting take on how those variations came to be.
Okay, I'm all ears. How does QGR explain those little temperature swirls?
Well, think about it this way. Even in a universe without a Big Bang, matter wouldn't be perfectly evenly distributed, right? We've got galaxies clumped together in clusters. We've got these vast cosmic voids.
Right, it's not like the universe is just one big, boring, smooth soup.
Exactly. And those clumps of matter, those galaxies and galaxy clusters, they have a stronger gravitational pull than the emptier regions of space.
Okay, that makes sense. More mass, more gravity.
Right. Now, imagine those CMB photons we talked about traveling through the universe for billions of years. What happens when they pass through one of those denser regions like a galaxy cluster?
Well, they encounter slightly stronger gravity, right?
Exactly. And that stronger gravity, it would cause them to lose a teeny tiny bit more energy.
Just like QGR suggests for photons traveling through any gravitational field. But in this case, the effect is amplified because those areas are denser.
You got it. And that slight energy loss, it translates into a slightly cooler temperature in the CMB. So when we look at the CMB map, those denser areas of the universe, they show up as slightly cooler spots.
Wow, that's so cool. So those tiny temperature variations in the CMB, they're like a map of the universe's structure, even billions of years ago.
Precisely. And that's one of the things that makes QGR so compelling. It suggests that the CMB isn't just a snapshot of the distant past, but this dynamic, evolving record of the universe's structure.
That's mind-blowing. But hold on, if we're seeing the universe's structure imprinted on its oldest light, doesn't that create a bit of a paradox? I mean, light travels at a finite speed, right? So how are we seeing the effects of structures that might not have even existed when that light was emitted?
Ah, you've hit on a really crucial point, and it gets to the heart of how QGR challenges our conventional understanding of cosmology. You see, in the Big Bang model, the CMB is like a snapshot of the universe as it was billions of years ago. But QGR suggests something far more radical.
Okay, I'm ready for radical. Hit me.
QGR implies that the relationship between the CMB and the universe's structure is far more dynamic and interconnected than we previously thought. It's not just a one-way street of information traveling from the past to the present.
Okay, so maybe we need to rethink our whole concept of time and distance in the universe if this theory is correct.
It's a very real possibility. And it's this potential to fundamentally change our cosmic perspective that makes QGR so incredibly exciting to explore.
I can see why this is such a big deal, but let's zoom out for a second. Why does it really matter which theory explains the CMB better? What's the bigger picture here? Why should this matter to someone who's not a physicist?
It's about much more than just understanding some faint light from the early universe, you know?
Yeah.
It's about grappling with the most profound questions humans can ask. Where did our universe come from? How did it all begin? What is its ultimate fate? These are questions that have captivated humanity for millennia.
And for decades, the Big Bang Theory has been the dominant explanation for these big questions. What does QGR offer that's so different?
Well, the Big Bang, it paints a picture of a universe that burst into existence from a single point, a singularity, an infinitely dense point. And ever since then, it's been expanding. It's a universe with a beginning, a middle, and potentially an end.
And QGR is saying,
What?
what, that the universe has always been here?
In essence, yes. If QGR is correct, then the universe didn't have this dramatic Big Bang beginning as we traditionally understand it. Instead, it might be eternal, perhaps even infinite in its extent. Just imagine that. A universe without a starting point, constantly evolving, constantly changing.
A universe with no beginning and no end. Well, it's both fascinating and a little terrifying, honestly.
It is, and it really highlights the power of approaching the universe with curiosity and an open mind. Questioning our assumptions, exploring new theories, embracing the unknown. These are the very things that drive scientific discovery.
Like that Carl Sagan quote, "Somewhere, something incredible is waiting to be known."
Exactly. And that sense of wonder, that drive to understand, it's at the heart of what we do as cosmologists. We're constantly pushing the boundaries of what we know, and the CMB, with all its mysteries, it's like this cosmic Rosetta Stone that just might hold the keys to unlocking even deeper secrets about our existence.
It really puts things in perspective, doesn't it? Like, all this time we thought we had the universe figured out with the Big Bang, and QGR comes along, turns everything upside down.
That's what I love about cosmology. It's always evolving, always finding new clues that change our whole understanding of the universe. And the CMB, with all its mysteries, it's a goldmine of information.
Yeah, it's humbling to think how much we still don't know, you know? It's like we've only just scratched the surface.
Exactly. Every new discovery has the potential to rewrite the textbooks. That's why it's so important to keep an open mind, to explore these alternative theories like QGR, even if they seem radical at first.
Because they challenge us to think beyond what we think we know, right? To question the Big Bang itself.